Hello, everyone. This is Tristan Sachsenweger, the lead developer of the ChargeFabrica simulation program. And I would like to give you a quick introduction for what is this program, how can you install it, and how can you use it. So right off the bat, this program is based on this publication over here, which if we go into it, it's Python-based drift diffusion simulator for perovskite solar cells, and it is built to handle both the electronic and the ionic continuity equations. So if you want to know more detail, I would recommend reading the paper, but just real roughly, we could see that it will solve for the Poisson equation, and also for the continuity equations for electrons, holes, and anions and cations, which we can then use to calculate the current densities, and finally things like the JV curve and stuff like that. Um, the underlying program which can solve these partial differential equations comes from a different Python package called PyPy, which is a finite volume PDE solver. And this is a very nice program. I would definitely recommend also reading into the details of how to set things up using PyPy if you wish to later on change the underlying physics of the model. Um, but I would like to get started with the ChargeFabrica program and how to install it for now. So right off the bat, if you want to install it, you can navigate down the GitHub page, and here you can find there is the installation instructions, and it requires a certain number of prerequisite packages. Those can be installed via pip quite easily. I think can also be installed via Conda, but this is the simplest technique. And then we should navigate ideally to a nice IDE, like in this case, I'm using PyCharm. And we could just simply inside of the Python console paste this command. And when we enter it, we could see that um, it should start solving or installing these packages. And in my case, these are already installed, but it will run through this. And once this is done, we can navigate back to the GitHub page, and then we have to clone the ChargeFabrica repository. This can be done just by copying this line. And then we can navigate to the terminal where our installation, our Python is installed, and we can then clone the repository. And this should then load up pretty soon over here. Yes, it updated. Excellent. And then I'm just going to follow, in this case, the quick start guide. So in this case here, we should navigate to the Drift Diffusion 1D ions with for a NIP perovskite solar cell. And we could basically just navigate then over here to this file. And I will real quick run through how the different parts of this code works. So effectively, we can import different material classes based on the names we give the materials, and we can store the material parameters inside the folders semiconductors and electrodes. So for example, for the perovskite, we can click into the perovskite, and we can see there is a nice list of different material parameters, like whether we should allow a charge carrier generation inside it, and the dielectric constant, the mobilities, and then things like the conduction and valence band levels, which we can get from the band gap and the electron affinity. And for perovskite specifically, we also have a mobile ions where we can define our mobility for the mobile ions as well as things like the coefficients for bimolecular and Langevin recombination. And finally, also things like the effective density of states for our material, and potentially also different doping levels if required. For the simple test, there is no doping enabled, but it can be entered if needed. And also, we have to define the mobile ion density at the beginning, and afterwards, then they will be allowed to shift around. So exactly, this is a hypothetical parameter where the mobile ions might have like a potential barrier to overcome, perhaps to move into the next material. But this is so far a bit untested, so I would leave it at 0 for now. But all of these material parameters can basically be imported with a single line of code after we get the ID. And we have to define then the pixel width, which we do with dx and dy. We can also import the absorbance data for the perovskite. And then to define the device architecture, we simply create, in this case, a 1D NumPy array. We can then add our different materials into this NumPy array by simply setting it into the ID. So all of the semiconducting materials effectively go into the NumPy array, and they can be placed anywhere where required. And in this case, it is a 1D array, but if we wanted to do a 2D simulation, all one would have to do is simply, for example, turn this into a 10, and suddenly it becomes a 2D simulation, and we could then, inside of the other areas, also import structural differences in the semiconductors. Now, for the boundary conditions, we have to define which electrode should go where. Now, for this, we also import the electrodes at the beginning, and they are defined a little bit differently. They simply have the work function as the defining characteristic, which we use to then afterwards calculate the electron and hole densities at the edge of the simulation using the ohmic boundary condition. Then we could basically calculate using the Lombard-Beer law, for example, the amount of generated carriers, or we could simply define a constant generation rate for the perovskite. And then this we don't really have to change much at all, actually. Um, we might have to define then, let's say, interfaces between the materials, which we can do using this line of code over here. We could define the interface between the titania and the perovskite and how thick the interface should be. And this we can then effectively give, for example, a separate Shockley-Reed hole recombination lifetime. And we can add more to it. We just have to effectively add new interfaces by just adding plus here. And then we can add further interfaces to this code line. Now we can head down. And this is not important. We don't have to change anything here. Also, we don't have to change anything here. This now comes the next section. Here we have to define if we want to enable Shockley-Reed hole recombination, we should define for the bulk what the bulk lifetime should be in seconds. And here we should also define the interface lifetime in seconds. And also we could define the trap energy levels, which currently for the bulk is defined in the mid bandgap range. And for the interface, it's defined as the level in between the LUMO level of one material and the HOMO level of the other material, basically in the middle of that for the interface. Exactly. And now we get into the main solver code. So we have effectively 5 state variables we're trying to solve for: the electrostatic potential and the 4 different carrier densities. Then using this code, we simply import the boundary conditions and we set them for the electron, hole, and the electrostatic potential. Then we have all of the different formulas for the different recombination models, whichever one wants to use. If one wants to add more recombination models, like for example, you want to have a bimolecular and also the Langevin recombination, one can simply add a plus here, and one can then also add the Langevin recombination to this line of code over here, and it should automatically enable it for you. So this is quite simple. And then we don't have to do anything here. This is already pre-calculated. These are the final equations, PDEs, which are being solved. So we have like transient terms over here. And then we have the diffusive terms for the charge carriers over here. And then we have the convective components, which is caused by the electric field or changes in the chemical potentials or changes in the effective density of states over here. We then add to it the generated carriers for the electrons and holes, and we subtract the recombination rates. And the bottom equation is the Poisson's equation over here, which again has a diffusion term. And then we add all of the different charge contributions on the different carriers, which are mobile, and the fixed dopant density over here. Now we get to the numerical side of how to solve these problems. Effectively, if the problem is very different, it might be worth it to start with a lower damping factor or lower time steps, as this could potentially help these solutions converge, especially if the problem is in 2D. And for the simple test here, we're using the Gummel process, where the process equation is solved first, and then the electrostatic potential is basically fed into the continuity equations, which are solved afterwards. Um, and Exactly. And once this is fully converged, we calculate the quasi-Fermi levels for the electrons and holes, as well as the electric field and the electron and hole current densities. So, and those can basically be exported and come into NumPy arrays. So at the fully bottom, we can then should just define some higher level things like which voltages do we want to solve for. And this is also an important code line where we can define the amount of multiprocessing we want to use. Now, oftentimes, having more CPU cores has a performance benefit. However, sometimes, especially also for the Newton solvers, it can be useful to step up the voltage more slowly. And that means also it would be more efficient to use less CPU cores sometimes. So one can, for example, define like 1 or 2 or 4 or 8 CPU cores, depending on the problem involved. But for the simple test, I'm just going to set it for 2, as it's just a demonstration. Effectively, after the program converges on a solution, the charge carrier densities and the electrostatic potential is effectively recycled for the next set of voltage steps. So this will help the convergence of later problems. And exactly, then down here, there is almost nothing which has to be changed. So now I would say we could just let's start running, um, and then I can explain real quick how things get saved then. So yeah. Um, this program also has the option to calculate things like external quantum efficiency over here, um, um, as well as the spatial collection efficiency with this program over here, where there is effectively this is solved by performing the short circuit solution, but also applying small scale perturbations to the generation rate, and then recording this small scale difference in the extracted current density. So These are also things which can be done, as well as preconditioning ions at a certain level, which can be done by effectively just loading in solutions from a previously run simulation, where we load in the anion and the cation densities, as well as the applied voltages. And then we can precondition the ions at a certain fixed value. And then for this simulation, effectively, it is important to note that we have to then disable the moving ions, because we don't necessarily want to move the ions from their preconditioned position. And this can also be quite useful if one wants to simulate, for example, VOC preconditioning, and then trying to see how does that affect the JV curve. So exactly. And yes, 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 yes. And then the plotting is done via uh, these code lines over here, where we have different plotting functions for 1D, 2D, or 3D problems. And effectively, we just have to load in the solutions from the outputs folder, which should get generated soon. And we can basically load in the different NumPy arrays over here. They just we don't have to change anything. We just have to note that for a 1D problem, we should use the 1D plotting file, and for a 2D or 3D problem, we should use the 2D plotting files, which have very similar formatting. We just have to basically give it the folder where the final solutions are stored. So maybe I can I refresh this? I think it should solve things soon. So as we can see, the simulation is running now, and yeah, I'll let it run to the end, and then we'll come back. Okay, and now we can see the first round of voltages have finished solving, and in this, after running this plotting code, we could basically see that we solve for the electric field strength, along with things like the generation profile, the electrostatic potential, and the recombination rates. And over here, we could see the charge carrier densities in 1/cubic meter. And then we can check at the interfaces how these things look like. The anions and cations will build up to a certain level. And in this case, they will screen the field such that the potential inside of the perovskite doesn't change very much. However, then at the interfaces, the potential will start to deviate again. As one can see, there is a larger electric field at the close to the perovskite interface, which helps carriers get extracted here. But then there is significant only kind of diffusive transport going on inside of the perovskite bulk material. And then over here, we can see the current densities, and this is the electron and hole current densities. In this case, we have the ETL on the left side, and it basically only has a electronic current. There is no hole current in there, which makes sense. And it is vice versa in the HTL side. There is only a hole current, but no electronic current. And if you add these two together, it will give us the total current, which should be basically a straight line, as we see here. And this then we can change this voltage using this bar over here, and that will then shift the voltage level applied. So it will dynamically adjust all of these curves. In this case, I didn't simulate much further, but one can run this all the way to like yeah, like 1.3 volts or something for most problems. And then we have over here the band diagram, which gives us the LUMO and the HOMO levels, as well as the quasi-Fermi levels, which are in between. where we can see how easy it is to extract the carriers, for example, in this case, the electrons. Yes, so this is basically how this works. And yes, so if one wants to do 2D simulations, one really doesn't have to change much. Like I said, one just has to go over here and change the number of elements in the second axis, and it's automatically 2D. And then one can decide where one wants to have which material. And I generally recommend ideally running this on a dedicated computing cluster, because especially the 2D simulations can quickly get quite computationally intensive. Um, and yeah, but I would at the beginning tend to ideally it's best to start testing a simple 1D problem first and make sure it works in 1D before moving on to a more computationally intensive 2D problem. So yes, so I hope this initial quick start tutorial helps a bit. And if you have any questions, let me know. Um, yes, so thank you very much for watching, and yeah, see you around. Cheers.